Welcome to the Electrical and Electronic Engineering Lecture Series. Your anchor person is Professor Michael C. Ndinechi. Our topic today is Pulse Code Modulation. Please follow me in this lecture series by subscribing to my channel at https://youtube.com/Ndinechi Michael C. Drop your comments in the comment section or reach out to me using my email addresses. You can also listen to my lectures on Introduction to Digital Communications in my channel at https://module017. Also, as a prelude to this lecture, I advise that you listen to my lectures on sampling theory, which I did on module 018, and the link is as given. Now, we start by looking at pulse modulation before we enter into the subject proper. The sampling theory provides a technique for converting a band-limited continuous message signal into a discrete time signal sampled at discrete points in time. The process of transmitting this discrete sample signal is termed pulse modulation and can be divided into two basic groups, namely analog pulse modulation, which is termed APM, and in analog pulse modulation, the samples directly modulate a periodic pulse train, which is also known as the carrier, with one pulse for each sample. And the second one is and then transmitted. You can now see why it's important that we know the computer arithmetic, binary numbers, which we had taken time to do treats in module 019. Now, the analog pulse modulation. Let us quickly trace through it before going into the pulse code modulation proper. There are basically three main types of analog pulse modulation, depending on the parameter of the pulse train in sympathy with the sample signal. The first one is the pulse amplitude modulation. Is varied by the sampled input signal. The shape or the width of the pulses remain constant. Pulse amplitude modulated signal will follow the amplitude of the original signal as the signal traces the parts of the whole signal or the whole wave. In the natural pulse amplitude modulation, a signal sampled at the Nyquist rate, which we had mentioned during our lecture on sampling. So the signal sampled at the Nyquist rate is reconstructed by passing it through an efficient low-pass filter with exact cutoff frequency. Though palm signal is passed through an LPF, low-pass filter, distortions still abound. To avoid this distortion, Flat top sampling is done as shown in Fig 1. This process simplifies the circuit design. If you look at Fig 1, see the topmost is the signal to be sampled. You can see it's a continuous wave. B is the pulses that are used to modulate it, which we call the sampling pulses. And 3C is the typical output. So you see 3, which is the sample output, shows that as the signal is varying, the height of the pulses is varying following the curve. When the curve go negative, the amplitude of the pulses will also follow it in the negative direction. At the end, the apexes of these pulses are noted as points and rejoined to recover the signal. The next one is known as the pulse width, some call pulse duration or pulse time modulation, noted as PWM or PDM or PTM. So here, the trailing or leading edge of the pulse or both may be made to vary as a function of the sampled input signal, thus modulating the pulse duration or width while the height remains unchanged. Amplitude limiters are used to make amplitude of this signal constant. Limiters clip off the amplitude to a desired level, and hence noise is limited. Now, if you look at the modulating signal and the pulses, which we call the carrier pulse, you see in A, we said the leading edge or the trailing edge. Now, in A, the leading edge is used to start the excursion. You can see how the pulse rises with the amplitude of the signal being high. You can see that the pulse is a bit wide following the amplitude of the pulse. So we note that the dotted line in brown shows the leading edge of the pulse, which we said that is the starting point. Now, that's what we are putting here, that there are 3 variations of pulse width modulation as illustrated in that Fig 2. A, the leading edge of the pulse being constant, while the trailing edge varies according to the message signal. Let's go back to see that A. A, the leading edge remains constant. So if you see the first pulse is the leading edge that starts, and the second pulse also the leading edge. Then B says the trailing edge of the pulse being constant while the leading edge varies according to the message signal. Look at that B again, where we used the purple dotted line to show that the trailing edge of the carrier pulse is being used. You can see the 2 purple dotted lines showing that it's the trailing edge that is being used to monitor the variation of the signal. And C, the center of the pulse being constant, while the leading edge and the trailing edge varies according to the message signal. So if we go back and see that C, you see the yellow dotted line showing the center and not the trailing or the leading edge that is being used. Well, the pulse amplitude modulation or the analog pulse modulation is no longer very much in use, even though we will continue to push and say where they are normally used. Now, pulse position modulation. The pulse position modulation, known as the PPM, is the scheme in which the amplitude and the width of the pulses are kept constant while the position of each pulse with here the transmitter has to send to keep the transmitter and the receiver in synchronicity. Each trailing of the pulse width modulation signal becomes the starting point for pulses in PPM. Hence, the position of this pulse is proportional to the width of the pulse width modulation pulses. Look at it. So now, when you get the pulse width modulation done, then to get PPM, you can see that at the end of every trailing edge, the PPM signal starts to pick the pulses. The first pulse trend up showing the PWM, the pulse width modulation, you see that at the trailing edge of the first pulse, denoted by dotted line blue, then the PPM pulse starts and rises. At the next leading edge, it falls. At the next trailing edge of the PWM, it rises. At the next leading edge of the next pulse, it drops. So it continues like that. So at the end of the day, the pulses are denoted as on or 1 bit, and it is these 1 bits that are composed and transmitted. So you can look at the comparison between the three of them. The PAM, pulse amplitude modulation, say under that, amplitude is varied. For PWM, width is varied. For PPM, position is varied. For the PAM, bandwidth depends on the width of the pulse. For the PWM, bandwidth also depends on the rise time of the pulse because it has to do with either the trailing or the leading edge. Then for PPM, bandwidth depends also on the rise time of the pulse because we say that PPM is an aftermath of PWM. So for PAM, it is an instantaneous the instantaneous transmitter power varies with the amplitude of the pulses, while in PWM, the instantaneous transmitter power varies with the amplitude and width of the pulses. And for PPM, instantaneous transmitter power remains constant with the width of the pulse. For the PAM, the system complexity is high. The equipment used in performing PAM has complex system. PWM and PPM, the complexity is low. Now for PAM, noise interference is high, but for the other two, noise interference is minimal. So PAM is similar to amplitude modulation, which we had already treated in some of our previous lectures, while the PWM is similar to frequency modulation, and the ppm is similar to phase modulation. So the transmission of analog pulse modulated waves involves a carrier modulation step in which the pulses are converted to RF pulses. Here, the samples or the modulated pulse modulated wave are used to amplitude modulate or phase modulate or frequency modulate a carrier before transmission. Say, you can listen to my earlier lecture on amplitude modulation and frequency modulation at module 007, parts 1 to 3, using the link stated. Or you go to my YouTube channel, https://youtube.com/@ndinechimichael look for module 007, parts 1 to 3, and listen to my lectures on amplitude and frequency modulation. Now, since transmission usually takes a very short time, the transmission channel can be used by other sampled messages between sampling times. Thus, pulse modulated system is operated normally as a time division multiplex system, TDM systems. In our subsequent lectures, we will look at this time division multiplexing and see how it really works. Now, we come to the main thing we are doing today, which is the pulse code modulation, otherwise known as the PCM. It was seen in our previous lectures that a low-pass signal of bandwidth B can be represented by its sampled values spaced by f of s equals 2b. That is our Nyquist sampling rate. If these samples are quantized, each quantized sample represented by a binary number, and these binary numbers represented by on-off pulse sequence. Then we have what is referred to as pulse code modulation. Now, what are the elements of this pulse code modulation? So, the basic elements that made up a PCM system are as shown in Fig 4. The system is similar to the pulse amplitude modulation system discussed earlier, but with the addition of a quantizer and an encoder at the transmitting end and a decoder and holding circuit at the receiving end. That is the block diagram for that. You see the transmitter has the analog signal coming in, is filtered, low pass filter, then sampled, then quantization and the encoding is done by the analog to digital converter circuit. Then the transmitter output goes out. At the receiving end, the transmitter output comes in to the decoder and the holding circuit. Sometimes it's called sample and hold circuit. Then it is filtered before being sent to the actual receiver, whether to the VDO or to serve as input to another circuit. Now, the continuous signal is first low pass filtered, sampled, and then rounded off or quantized to the nearest predetermined discrete amplitude level to give a digital signal that is discrete in time and amplitude. The encoder converts the quantized signal samples to digital code word on a code word per sample basis. The analog signal to be transmitted over a PCM system is first split into a number of standard quantities. So when we say A equals to N, so it could be 2 raised to power 2, 4, 2 raised to power 3, 8, 2 raised to power 10, 2 raised to power 5, 32, 2 raised to power 6, 64, like that. So each of these quantum level is separated from the adjacent level by a step size known as delta. A step size delta. Suppose there are X digits or pulses in a code word, and each having one of Y discrete values. Then for binary PCM, Y is equal to 2. So that A equals that. If you do little mathematics, you see that log 2A is equal to X. Now, it can be different levels, not just binary levels, in which case ourselves to base 2. The number of binary PCM bits transmitted per sample is determined by various variables, which include 1, the maximum allowable input amplitude; 2, the resolution, that is, the minimum voltage other than 0 volts that can be decoded by the digital to analog converter, DAC, at the receiving end; and 3, the dynamic range. This dynamic range is the ratio of the largest magnitude to the smallest possible magnitude that can be decoded by the digital to analog converter. Now, we come to a very important portion here, which is the signal quantization. The digitization of analog signals involves rounding off of the values to approximately that of the analog signal. We will see that shortly in a drawing. You understand it better. Sampling chooses a few points on the analog signal, and then these points are joined to round off the value to a near stabilized value. This process is known as quantization. Now, consider a waveform shown in Fig. 5. The first sample at t equals 0 has value 2 in decimal, which corresponds to 010 in binary. The second sample at t equals ts has value of 4 in decimal, which is 100 in binary, and so on. Now, the first sample, 010, is sent through the system as a 0 amplitude pulse, followed by a pulse of amplitude A, and then followed by another 0 amplitude pulse. So it's 010. The same procedure is followed for the next sample. In this case, a pulse of amplitude A followed by 2 zeros, and so on. Now, let's see a demonstration. Look at the figure A. We have, just a typical analog signal, which we are seeing in black line. Now, this analog signal is quantized, and we said we have levels, and the level is separated by delta, which in this our case we have by 1. Now, at the starting point 0, we are looking at Fig. A. At the starting point 0, the signal is almost at 2 or closer to 2 than 1. So the quantizer sees it as 2. So because it is using 3 bits, code word to represent information. It sees it as 2. So it converts 2 to its binary equivalent, which is this 010. If you look at figure B, you see the first blue pulse that it has stamped it 010 from 0 to TS. Now, it goes again from at point TS, the signal is closer to 4 than to 3. So it rounds it off to 4. And 4 in binary is 100. You can now see the second blue pulse in Fig B that it rounds it off to 100. Then it comes to 2TS. It sees the signal again closer to 4. It now puts up another pulse from that 2TS as 4, which is again 100. Then it comes again at 3TS. It sees the signal. Now this signal is closer to 3 than to 2. So it takes it as 3. You now see the fourth blue pulse on Fig B that it sees as, that starts at 3TS. It sees it as 3, and 3 in binary is 011. So now your system has quantized that signal given in Fig A into binary bits. Now, it wants to transmit this binary bit. Transmitting this binary bit will be transmitted as on, off, or 0 or 1 bit. So it now takes the first blue in Fig 2, the first blue pulse, 010. So it now transmits in Fig C, we now transmit a pulse with amplitude A, 0, then 1, which we are showing in, we call that color pink, then another 0. You see, it has transmitted that first pulse, first blue pulse of 010. Now, the second blue pulse, which is 100, it transmits a 1, which is the second pulse, purple color we are seeing, that starts at TS. It will transmit a 1 and a 00. 0 could be blank space, 0 could be a negative pulse going down. In this case, we are using blank space. Then from point 2 TS in Fig C is transmitting the third blue pulse in Fig B. So it transmits a 1, then 2 blank spaces. And the third one and the fourth one, which is 3, 011, it transmits a blank 0 and 1 pulse and 1 pulse. So you see, your system has been able to quantize that signal in Fig A into pulses in Fig B and into binary digits or pulses in Fig C. So that Fig C is the pulse code modulation we are talking about. Now, we go quickly to now see what is happening. At the receiving end, the samples are demodulated by essentially the reverse set of operations used at the transmitter. The reconstructed signal is then low-pass filter to eliminate sampling harmonics. Since the reconstruction cannot be perfect, a difference exists. between the reconstructed signal and the ideal signal. This difference is referred to as the quantization error. Very important to note. This error is associated with additive noise, which is a random process, otherwise referred to as the quantization noise. It is clear if we go a slight bit. If you look at Fig A here, where we have the analog signal from 0 to TS, we say that from 0, it is not up to 2, it is not 1, but it is closer to 2. We now took it to be 2. Now, that difference between the exact 2 and where the signal is introduces an error. Likewise, at TS, we say it's closer to 4 than 3, but it is not up to 4. So that difference introduces another error. At 2TS, it is closer to 4 than at TS, but we still called it 4. So there is another error introduced. So these errors add up and occur in the final reconstruction as noise. That is what we say that the error is associated with additive noise, which is a random process, otherwise referred to as quantization noise. So quantization noise is most serious when the signal is small and covers only a few of the lower quantizing intervals. Non-uniform or non-linear quantization. There are two types of quantization known as uniform, as the one we have described above, and non-uniform quantization. For instance, in voice communications, the lower amplitude waveform occurs more frequently than the large amplitude waveform. Get it right. When you are talking, the difference between the highest amplitude from your voice and the lowest amplitude may be very small. Your voice is likely to be, close to flat. So it becomes difficult for you to now do this quantization. The signal may fall within the same amplitude level. To get what we are saying here very correct, if you look at that signal figure A, what if this signal starts between 1 and 2 and till the end it remains between 1 and 2? There are no peaks that crossed 2 to go to 3. You see that if you quantize that, what you have will be just 2, 2, 2, 2, 2, 2. That is 0, 1, 0, 0, 1, 0, 0, 1. The pulses will be the same. So if you transmit that at the receiving end, you will just have a flat, signal, which will not be true representation of the original signal. So we call that, for us to now treat that, we see it as a non-uniform quantization because we have to do something to vary it, to make it look, the amplitude difference look big. That is why we said in voice communications, the low amplitude waveform occurs more frequently than the large amplitude waveform. Therefore, the use of a uniform quantization, as described above, for such signals will result in unacceptable poor signal quality to noise ratio, denoted as SQ, and R for low amplitude signals, unless the delta is made to be very small. The delta is the step increase. That is, that's increase one space between 1 and 2 in that fig A. So making delta very small again leads to an increase on code word length and increased bandwidth of transmission. So you cannot continue to make delta very small. It has its own side effects or disadvantage. An alternative to making a very small is to employ a non-uniform quantization. This requires that the quantization steps for the low amplitude signals be reduced so that more codes are used to represent the low amplitude signals so as to increase the signal quality to noise ratio. At the same time, the codes for the large amplitude signals are reduced with attendant reduction in signal quality to noise ratio. This process of doing this non-uniform quantization is called compounding. Compounding. So, what is this compounding in PCM systems? So that analog to digital converters, ADC, for non-uniform quantization are not available in practice. So a technique used to effect non-uniform quantization is to precede the sampler with a compressor while an expander follows the LPF at the receiver. This allows the transmitter to continue to use linear quantization ADC to transmit. So you see, the addition of the compressor and the expander makes us to allows us to use analog to digital converters that are used for uniform quantization, which is commercially available. So say this allows the transmitter to continue to use linear quantization ADC to transmit. The net effect on the signal is as though nothing were done except for the effect of quantization noise. This combination of compression and expansion is known as compounding. We have said that. So the compounder compresses the large amplitude analog signal while the expander expands this same signal at the receiving end. That is, you compress when you're transmitting, at the receiving end, you expand. Digital and analog compounding systems are commercially available. Two types of analog compounding techniques are in use to approximate the logarithmic function of the signal, and they are the A-law compounding technique and the mu-law compounding technique. In A-law compounding technique, uniform quantization is achieved at A equals 1. A-law technique is extensively employed for PCM telephone systems and is given as the equation V out over V in equals 1 plus length in brackets A, which is amplitude, times V in over V max all over 1 plus ln A, when we say the natural logarithm of that. And this is acceptable for V in over V max lying between 1 over A and 1. And V out over V in is equal to A into V in over V max all over 1 plus natural log of A for V in over V max lying between 0 and 1 over A. We call that equation 2, where V out is the compressed output voltage, V in is the instantaneous input voltage, V max is the maximum uncompressed analog input voltage, V out over V max is the normalized output voltage, whereas V in over V max is the normalized input voltage. So in the mu law, uniform quantization is achieved at mu equals 0. Remember, we say for the A law, it is achieved at A equals 1. For the mu law, it is at mu equals 0. The constant mu determines the severity of the compression's characteristics or the range of the signal power in which the signal quality to noise ratio is relatively constant. Voice signals often require that mu lies between 100 and 255, depending on the code word length and the dynamic range. It is used extensively for speech and music signals and is given as V out over V in equals natural log of 1 plus mu into V in over V max or over natural log of 1 plus mu. Call that equation 3. Or simply put, y is equal to then 1 bracket 1 plus mu x all over then bracket 1 plus mu, where y is equal to V out over V in and x is, that is, if you substitute that in equation 3, you get equation 4. So typical curves for certain values of mu. The type of compounding law in use depends on equipment. It will depend on the choice you are using. The A law gives a flatter signal quality than the mu law for a given range, but the small signal quality is generally inferior. So you see that for the compressor, fig A, at the receiving end, the expander is also as shown. So you say that that is the input characteristics. So now we come to what we call the differential pulse code modulation, otherwise known as DPCM. So DPCM is similar to ordinary PCM, but the samples that are highly correlated when encoded by ordinary PCM technique usually leave redundant information behind. In other words, DPCM makes use of the memory that exists between samples when analog sources are sampled. For example, speech signals will have considerable memory between samples taken at high sampling rate. Because of this memory, the value of a future sample may be predicted from the current sample. The prediction for a given sample is then subtracted from the actual signal sample value, and the quantized and the encoded error is transmitted through the channel. At the receiver, the encoded error samples are decoded and added to the predicted sample. These samples are then low-pass filtered to reproduce an approximation to the analog signal that was originally sampled at the source. In this manner, fewer bits per second can be used to transmit the information through the channel. But note, DPCM system has not found wide acceptance because of complications in the encoding and decoding processes, which appear to outweigh any advantages that may have been gained. So the important one here is the delta modulation. It can be recalled that the sampling rate of an eyepiece of a signal should be higher than the eyepiece rate in order to achieve better sampling. And my question is, can you remember why? Tips. When we did sampling, we talked of having, when you sample at the eyepiece rate, that is 2B, you will have your signals, but your filter has to be an ideal filter to get that. Because ideal filters are not practical filters, then you need to sample at a rate a bit higher. That a rate bit higher introduces what we call the gap band. That gap band allows you to make use of practical filters to recover your signal. If this sampling interval, as in DPCM, is reduced considerably, the sample to sample amplitude difference is very small, as if the difference is 1 bit quantization, then the step size will also be very small. This type of moderation, where the sampling rate is much higher and in which a step size after quantization is of a smaller value, is termed delta modulation. In its simplest form, 1 bit is sent per sample to indicate whether the signal is larger or smaller than the previous one. This system has the attraction of extremely simple coding and decoding procedures, and the quantizing process is also very simple. We will see shortly. However, the delta modulation cannot handle rapid amplitude variations between samples, and so quantizing noise is very high unless the samples are very close together. So let's see an illustration. Now, if you look at a typical signal denoted in yellow, what delta modulation does is it puts up a step around the signal. That step has a differential or height, delta. If you look at, to your left, you see the delta sign in red showing the step size. And what you are seeing is like step. So let's look at the first X, or the first step. We marked it by X. Then the next X is a step higher than the first one. It automatically calls it a 1 because it is higher. The next step is higher, it marks it another 1. The next step is higher, it marks it another 1. It continues like that. But if we look at the third X along that yellow signal, you see that that step is lower than the step before it. It marks it 0. The next afterward, that X is higher. It marks it 1. The next after that one is lower. It marks it 0. The next after is 1 is higher. It marks it 1. The next after is 1. It continues to mark it higher until when the signal starts returning, each one is lower. Each next one is lower than the one before it. So it continues to mark it 0 until it gets to the point where the signal starts rising up again. The next one becomes higher than the previous one. It continues to mark it 1. So at the end of the day, you see that for data modulation, this string of ones will be what will be transmitted, just as we saw in the PCM. Now, we want to exercise our brain. Say, quick exercise. Now, suppose you are using a computer that makes use of 4 bits as word length. Can you tell me how many registers will be required to hold the bits to be transmitted? Now, look at the bits to be transmitted, and say it's 4-bit word length. The system you are going to use that is 4-bit word length. So, and we know that from our previous lectures, computer lectures, we know that bits are stored in registers or computer memories. Please follow me on a Friday lectures where we will look at computer memories and registers. You will see exactly how these 11 bits we are talking about will be stored in the computer or any digital device you are making use of. So the second question is, give us the hexadecimal equivalent of data to be held in each register. We repeat. The question 1 says, how many registers, if this is a 4-bit word system, how many registers will we have in transmitting all these string of binary numbers? Now, what will be the data that will be stored in hexadecimal in each of the register? You can see that the essence of treating computer arithmetic or computer number system is not just to get to ones and zeros, but for ones and zeros to make meaning to us. Because if we see ones and zeros, it will definitely not make meaning to us. But if we can, as humans, interpret that ones and zeros, then we begin to appreciate why computer is a very interesting device. Thank you for listening. Please join me again in my next lectures. Tomorrow by this same time, I will be talking on internet technology simplified, so that when you see internet, when you hear internet, you will be able to really appreciate what is happening and see how simple what you think that is complex is. So please, I look forward to seeing all of you by 8 o'clock tomorrow evening, listening to my lecture on internet technology. It is not just for lectures. Any person who wants to advance his or her knowledge on internet technology and what it's all about should endeavor to join me tomorrow evening by 8 p.m. to understand more. Thank you for listening, and don't forget to make your comments, ask your questions in the comment sections. I will get to that place and answer you. Thank you.